Yeah. So, we have done a problem. Let us do another problem, and this solving problem will help you in assessing the situations that you have to keep in mind. Not only in mind, the values will give you idea really if you are working in industry. So that more and more problems you solve, more and more you come across with the ideas, with the real applications, right? So let us then do the similar problem. A tubular heat exchanger and a plate heat exchanger is separately used to heat water. Diameter of the tube is 15 millimeter. Gap in the plates is also 15 millimeter. Water has a viscosity of 1.2 into 10 to the minus 4 Pascal second and density of 1000 kg per meter cube. For both the heat exchangers, NRE is said to be 5000. What are the average velocity and pressure drops for the two cases, right? I think this we should change, this should be R capital. So by mistake it was, so R capital should be, right? So in the previous one also it was there RE, but I did not change. So you please change that R is capital. Okay. So we repeat, a tubular heat exchanger and a plate heat exchanger is separately used to heat water. Diameter of the tube is 15 millimeter. Gap in the plates is also 15 millimeter. Water has a viscosity of 1.2 10 to the minus 4 Pascal second and density of 1000 kg per meter cube. For both the heat exchangers, NRE is said to be 5000. What are the average velocities and pressure drops for the two cases? If you remember, in this previous problem, we also dealt with a similar one, and we saw rather that it was for a juice and the property values were different a little, may not be very widely different, but different, and we saw that tubular heat exchanger had higher velocity as well, the pressure drop compared to those of the plate heat exchangers, right? And this was true when the flow was not laminar but somewhere intermediate. We took, if I remember, we took around 3000 as the Reynolds number, but here we have taken Reynolds number to be 5000. So it is no more that laminar flow, that is what we have done for the previous one for pressure drop calculation, right? That Hagen-Paiseli delta P we cannot directly use, right? I hope you have, by this time you have done many other problems solutions also. So here instead of Hagen-Paiseli, some other formulation we have to use, and that I hope you have come across, or you can understand or make out that what could be that, right? So that is why again and in this case we are comparing, or rather there can be a comparison between the fluid. In the earlier case it was a juice, and in this case it is water, and viscosity is and densities are also quite different, right. So that should also tell on both the velocities as well the pressure drops, right. Now let us look into how far really it is telling on the values, right. So let us see that whatever has been told, we have been said that for tubular heat exchanger, the given things are diameter of the tube is 15 millimeter is equals to 15 into 10 to the minus 3 meter, right. Viscosity of the fluid or water mu w is 1.2 10 to the power minus 4 Pascal second, right. And Reynolds number given is 5000, right, and density, that is rho of water, given is 1000, right. So since it is a pipe flow through the pipe, we can directly use that relation of NRE is equals to dV rho by mu, right. So D is given as 15 10 to the power minus 3. V we have to find out. Rho is given 1100. Mu we have not 1100, it is 1000, and mu we have 1.2 10 to the power minus 4 Pascal seconds, right. So if that be true, then let us also take this, that let us also take, okay, V is equals to, of course these are all V average. V average is equals to, then NRE is 5000 into 1.2 into 10 to the power minus 4 over 15 times 10 to the power minus 3 times 1000, right. So this has gone there, V is there, V average is so. So let us look into how much it is. It is 5000 into 1.2 into 10 to the power minus 4 is so much divided by 15 divided by 1000 divided by 10 to the power minus 3. It is 0.04 meter per second. If you remember, when it was a juice, to my memory, it was much more than this. Velocity was much more than this. It was not 0.04 somewhere. It is at least 4 or 5 times greater than that, right. So just check, okay. So velocity has become so much, and now let us look into the pressure drop, right. Now since it is not the laminar flow and the flow is turbulent, 5000 turbulent. So, we need to apply we need to apply that relation where it is with the fanning friction factor. So, delta P is equals to 4F, right, rho L by D V square by 2. If we remember correctly, we average by 2. So, this was the fanning friction factor, right. So, what we need from the fanning friction factor chart, Moody's chart, that if we remember that we had said NRE versus F, right, that was given for different epsilon value or epsilon by D, these values were there, and from the Moody's chart we can find out what is the value of F, right. Since we do not have here that Moody's chart, let us assume that corresponding to NRE equals to 5000, right, the value of F, of course, we need to know the epsilon by D. The value of F say can be 0.01, right. Let us assume it. Then we can find out the value of delta P, that 4 into 0.01 into rho is 1000 into L was given 10 meter. If I remember, let us look into, right, 5000 15 millimeter diameter of the tube, same density. This was okay, gap in the plates is so much. Okay, then so it is 1000 into 10 meter over into V average, right, L by D. D is 15 into 10 to the minus 3, right, and this is 2. V average we came out to be 0.04 square, right. So, if you look at this, then we can see that 0.04 V square. So, it is square into 10 into 1000 into 0.01 into 4 is equal to divided by 15 divided by 2 divided by 10 to the power minus 3, 10 to the power minus 3. So, this came to be equal to 21.33 Pascal, right. And just check corresponding to this velocity delta P for the turbulent flow we have done for the laminar or intermediate, when the flow is intermediate, there we have found out that what is the value of pressure drop and what is the value of velocity. Now, we have also found out of course the fluid is different, that is for water what is the value for this, right. If there is a little time, we will go back to the previous problem and do this same for the pressure drop, because velocity for pipe flow will also remain more or less similar. Okay. Now, for tubular heat exchanger it was like that. For plate heat exchanger, if we look at that value NRE, and in this case of course plate heat exchanger like the earlier one, we say that this is the flow through slit, this is flow through pipe and this is flow through slit, right, because the gap is very small and it is moving through that, right. So, for plate heat exchanger we can write that NRE is equals to 4 del V rho by mu. So, it is 4 and del same 2 del is 15. So, del is 15 by 2, that is 7.5 millimeter. So, we write 4 into 7.5 into 10 to the power minus 3 into V. We have already found out that is to be V we have to find out. Okay. So, V into rho is 1000 divided by mu is 1.2 into 10 to the power minus 4. Therefore, V comes out to be NRE is 5000 into 1.2 into 10 to the power minus 4 divided by 4 into 7.5 into 10 to the power minus 3 into 1000, right. So, this comes out to be, let us see how much it comes out. So, 5000 into 1.2, right, into 10 to the power minus 4 divided by 4 divided by 7.5 divided by 1000 divided by 10 to the power minus 3. It is 0.02. It was in this case 0.04, in this case 0.02 meter per second, right. Now, the question comes for the delta P, right. What will be the delta P? Now, if we see that delta P through the slit, the expression for that, it is again in this case, this for the pipe it was assumed to be 0.01. Now, for the slit, let the value of F from of course NRE versus F corresponding to that, we can get value of F to be equals to say 0.015, right. So, if it is like that, then we had earlier assumed it is 0.01. So let us say it is 0.015, right? So then we get that delta P is equals to that 4f rho, right, L by D V square average by 2, right, and this is of course not 4f, this was for pipe. So for slit we write 2f rho V average square, right, L divided by 2 into 2 del, right. So this is what is for the flow through the slit. So that comes to be 2 into 0.015, right, into 1000 into V average we have found out to be 0.02 into L was 10, and this is 2 into 2 del, 2 del is 15, right. So 15 millimeter, so 15 10 to the minus 3, right. Now if we look at this value, calculate it, then it comes to be say 2 times 0.015 times 1000, right, times 0.02 square times 10 is equal to this divided by 2 divided by 15 divided by 10 to the power minus 3. Right. So that comes to be 4. Right. This is equal to 4 Pascal. Right. So here it was again high, here it is low. Now I said that the two cases we have dealt with, both for laminar as well turbulent. But I said that if we look at the previous problem where it was laminar or not laminar, it was intermediate, and in that intermediate the values of delta P and V what we got, that was for the your juice, apple juice, if I remember, right. Now if we do the same for turbulent one for the apple juice, let us look into how the value is different, right. Let us look for turbulent how the value is different. Let me open that. This was the problem. Right. So instead of 3000, okay, let us do for the yeah. So what we get that for turbulent flow for tubular heat exchanger, right, NRE for apple juice, apple sauce is equals to dV rho by mu, and values of du was, we have to find out V. So, V is NRE mu over d rho, right. So, NRE is in this case 5000, mu it was 7, 10 to the power minus 4, right, and d was 0.015 and rho was 1100, right. So, if we see what is the value, right, it is 5000 into 7 into 10 to the minus 4 divided by 3.5 divided by 1100. It is 9 10 to the power minus 4, 9 10 to the power minus 4 meter per second, right. So, velocity has gone down, right. So, 5000, when the Reynolds number is so high, 5000, so this is 7 10 to the minus 4, right, 0.015 and it is 1100. So, 5000 into 7 10 to the minus 4, actually we might have done something wrong. Let us look into once again. It was 7 10 to the minus 4 viscosity, yes. So, the value should not go so low because Reynolds number has gone up. So, 5000 into 7 into 10 to the power minus 4, right, divided by 0.015 is equal to divided by 1100. 0.21, that's what, not so, this was wrong. It is 0.212 meter per second. And if we look at what is the value, it was 0.127. So, velocity has gone up, right. Similarly, if we look at the pressure drop, delta P was 4F rho V square by 2 to L by D, right, and it was 4 F, we took say 0.01, right, into 1100 into V we got 0.212 square by 2 to L is 10 and D is 0.015, right. So, if we look at that, then also we see that this is 4 into 0.01 into 1100 into 0.212 square is equal to this into 10 so much divided by 2 divided by 0.015 is equal to 659. So, it is 659 Pascal, okay, 0.17, okay. So, 659, and if we look at what is the value for delta P, it was 126 Pascal. So that means when from laminar flow, or it was not laminar, intermediate. So when it is like that, from intermediate to the other one, that is turbulent, it went up, the both the velocity and the pressure drop went very high, right. Thank you.